at the end of class last time, or last time in class, we looked at the alignment issues, and actually you brought up you had a question about the program counter, and I kind of glossed over the answer, but there's more to that question than we spoke about last time. So I want to look here at figure 12.24 to show you what the issue is. Now, here's the thing. We said that if you have a 2-byte data bus, then you get 2 bytes at a time. But when you do fetch in the fetch, decode, increment, execute, repeat in the von Neumann cycle, when you fetch, you only fetch the instruction specifier, which is 1 byte. So you get the extra one for free. By free, I mean it comes at the same time, and so no time penalty if you have a 2-byte bus. So what we did is we saved the extra one, and then if we ever have to do another fetch, then we know that we can just get it straight from the... And what we said was that, well, how do we know whether we have fetched or not? Well, we can know because whether the program counter is even or odd. But now here's what's interesting, and which I glossed over. What happens, that's what happens if you do just a fetch and a decode and an increment and an execute, and execute does not change the program counter. Are you with me? Because if execute changes the program counter, now what's it going to do? It's going to change it. It might be even or odd, and we might be mistaken as to whether it has been prefetched or not. Do you see the problem? So not only with a system like this, with a 2-byte data bus, not only do you have to align data, but you also have to align program statements. Not only do you have to align data statements, you have to align program statements. And look here on figure 12.24. You see in part A, without program alignment, there's an example program here. But now what we've done in part B with program alignment is we have had to align the main program to start at an even address. Now, why did we do that? Why did we have to do that? Why did we have to align the main program to be at 0004? Yes, well, what has to happen is whenever the program does, whenever the program executes the first instruction in main, when it fetches that, it's got to know that the operand specifier at main is even and it hasn't been fetched yet. Are you with me? Yeah, so here's the thing. The first instruction in main, in the first instruction in main, the instruction specifier has not been prefetched because we're branching there. So it could not have been prefetched. Are you with me? So when we branch to main, so what does this mean? This means we have to branch to a what? We always have to branch to a place that is an even address. Because if we don't branch to a place that has an even address, the hardware will assume, oh, it's odd, it's been prefetched, and it will take some garbage value from the temporary register. Do you see what I mean? So the question is, how do we make sure that main is at an even address? Well, we do a .align to make sure that main is at an even address. But once we do the .align to and main is at an even address, now take a look at the else. Else is no longer at 0018. Now else would have been what? It would have been at 0019. But now if we're going to branch to else, now we have to make sure that else is at an even address. So the whole thing of it is that the target address of a branch has to be at an even address. Otherwise, the hardware will mistakenly assume that on the next fetch, the there has been a prefetch. A prefetch has occurred when it really hasn't. And now but now how do we align the else? How do we align the else part? We can't do a dot align, because what would a dot align do? It would fill in. What bits get stuck in there with a dot align? Zeros, yeah. But if it tries to execute if it tries to execute a 0, that would actually, 0 happens to be the stop instruction. Yeah, you remembered that. Yeah, and so we don't want to stop. So what we need is a no-op, N-O-P. This is a common instruction. It's always spelled this way, N-O-P, and it's pronounced no-op.
Is that a 0 after it, or
a no-op is a unary instruction.
But it says no-op.
Oh, you're right. Well, okay, yeah. Okay. Now comes something that's kind of ugly. I apologize in advance. In order for this to work, in order for this to make sense, no-op should be a native no operation instruction that takes place, that only takes one cycle. Do you see what I mean? There needs to be a no. And in all real architectures, that's the case. We didn't have room for one in the instruction space of the PEP9 computer. So no-op 0 happens to be a trap instruction, which means you gotta, and you know how trap instructions work, you remember that? So it puts the process control block and does that, and then it just goes back. And so all the time savings that you would get by doing this, they all go away because we don't have a one cycle no-op instruction native, but this is the idea. In a real system, no-op would be a one cycle. In a real system, no-op would be a one cycle instruction that you could just throw in there that would just, when it goes there, it would just go to the next one. And it would be very cheap to execute. It would only cost you one cycle. Admittedly, in PEP9, it would cost you more than one cycle, so it's not realistic. But in a realistic, in a real processor, that's what it would do. But the point is that you need no-ops. You need no-ops to align programs as well as data because of this prefetching that we have with the, with the 2-byte data bus.
So you can use it in place of a line?
Well, you have to use it in place of a line whenever you are aligning targets of the program.
You said for data too?
No. For data, you always use the dot align. Yeah. Yeah, question?
Is this program alignment taken care of by the compiler?
Yes, and obviously, unless you are yourself writing in assembly language, then you would have to be aware of these issues. But obviously, what happens is when you program in a high order language at HOL6, then the compiler has to be aware of all of these alignment issues, and it has to put in the proper dot aligns and the proper no-ops. And so it has to know about the architecture. It has to know about even the organization of the CPU. And what happens is, if you read the manuals, these hardware manuals, there's always a chapter in the CPU documentation about alignment, about performance issues and alignment. And so they specify, they give you rules, blah, blah, blah. And then the compiler writers take those rules and they implement them in the compiler to do it. And typically what happens is, and by the way, this is a great example of what trade-off, the fundamental trade-off. Space-time, because it takes more space. But by taking more space and aligning it, we get faster time. And it's all processors have these alignment issues, because there's no processors, no commercial processors only have a 1-byte data bus. That's a super tiny example, but just to show us the concepts. See, we can still explore these concepts. All right, and there's other things you can read in the book. There's a discussion also about what happens if you do a call, because call is another one that changes the program counter. And so when you do a call, that changes the program counter. So you got to worry about alignment issues there also. But the thing of it is that call is a non-unary instruction, and it takes 3 bytes to store. So anyway, there's a few little complications that you can read about there. Now, our main topic that we want to do today is cache memory, but before we do that, I want to go through some ideas here about how big is a computer. Now, are you guys familiar with the fact that, see, as the years roll on, I sometimes forget how far back you guys go. But are you guys, you guys remember the 32-bit computer, 64-bit computer thing? You with me on this? I mean, that's been a big discussion. That's the latest one. It used to be, they started off to be 8 bits and then they were 16. And they used to be, oh, a 16-bit computer or a 32-bit computer, you know, the question is. And so the big question is, what is an n-bit computer? What is a 16-bit computer? What is a 32-bit computer? What is a 64-bit computer? Okay? So what is an n-bit computer? Well, here's what an n-bit computer is. Now that we've seen the MDR and the MAR, the n-bit computer, n, like in a 32-bit computer, is 32 bits in what key register, in what key part of the CPU? What does it say? The MAR. The MAR, however many bits there are in the MAR, that's what the n is in an n-bit computer. So how big is this? How big is the PEP9 computer? How many bits are in the MAR in PEP9? No. We have, what do we have? We have MARA and MARB. So how many bits are in the MAR?
16 bits.
16 bits. 2 bytes, 16 bits. Now what does that mean? That means that we can access 2 to the 16 bytes of memory. Are you with me? So an n-bit computer, so that's an example. An n-bit computer has n bits in the MAR and in the CPU registers. So normally the register size in the CPU, the registers in the CPU, are the same width as the MAR, and that's the width. So now what would a 32-bit computer have? The MAR would be what? How many bits? A 32-bit computer would have how many bits in the MAR? 32. So it could access 2 to the 32. Now how much is 2 to the 32? Now do you remember how to do this? Do you remember, yeah, do you remember the mega, do you remember the mega, do you remember the kilo, mega, giga? So 2 to the 10, that's the what?
Kilo.
That's the kilo. 2 to the what? 20th is the what? Mega. And 2 to the what? Is the what? Giga. So 2 to the 32 is how many gigs?
4.
Yes, it's 4 gigs. So that's why, and so a 32-bit computer can access how many bytes of memory? 4 gigs, 4 gigabytes of memory. Is everybody clear on this? So do you see why they had to go, do you see why that wasn't enough? For many years that was enough. Bill Gates made a famous statement. Nobody will ever need more than 640 megabytes or something. It's some ridiculously low number, you know. You know, and then all of a sudden 4 gigs wasn't enough. So the next big transition was from 32-bit computers to 64. All right, but as we've seen, the data bus can have any number of bytes. So the registers in the register bank at level LG1 could have less than n, and then you'd have to have multiple cycles to do like we do in PEP9. The data bus could have width greater than n, and the address, the data bus could have width greater than n. So you could, you know, instead of prefetching 4 bytes, we could prefetch 16 bytes and just extract the 4, you know, the 4 that we needed. Okay? And furthermore, the address bus width can typically have less than n. So if you have a 64-bit chip, do you think that they use actually 64 lines are all used? The answer is no, because look at this table. Look at this table in figure 12.25. If the MAR width is 8 bits, then you can access 256 bytes. All right? And if the MAR width is 16 bits, you can access 64 kilobytes. That's the PEP8, PEP9. And then if the MAR width is 32, you can access 4 gigabytes, which we just calculated that here. But look, in a 64-bit chip, if you had all 64 lines, you could access, how many is that? 17 billion gigabytes. And there's no way you can have that much memory on in a device. So consequently, they don't use the address space. They only use a small fraction of the total possible address space, and they don't even bother putting all 64 address lines on the system. But as you need more, as memory gets smaller and smaller and cheaper, and you can access more and more memory, then they free up, and then they'll add an extra address line, and that'll double how much memory they can access in a real system. And here's an interesting historical how it evolved in history. The very first chip, the very first processor on a chip was the 4004. The register width was 4 bits. And that was in 1971. Then there was the 8008, which was an 8-bit chip in 1972. Then the 8086 came out in 1978. These are all Intel chips. 1978, 16-bit, and then in 1985 was a 32-bit, and then 2004 was 64 bits. Now, the next big thing way to improve the performance, other than increasing the bus width, is with cache. Now, cache this is really important. All processors have cache memory. And so it's really an important concept to understand at this hardware level. Now, so let's think about what is it that slows us down? What is it that takes time in the CPU, in the organization that we've done? What is it that takes time? Well, it takes a certain amount of time to do a computation, right? So, and what part of the CPU does the computation? Does the heart of that actually does the computing? The ALU. So the ALU is a combinational device, so it takes a certain amount of time it's a combinational device. So it takes so many gate delays to go through there and then to go back up. So in one cycle, it goes through the ALU, it does a computation, it puts the results back in the register bank. All right? So it takes time to do the computation, but also, what else took a lot of time? Reading from memory. So not only does it take time to do a computation, it also takes time to move information from one part of the system to another part. Are you with me? So there's always those two aspects of it. So here's the idea behind cache. Well, first of all, in practice, in our simple little model, it just took 3 cycles. In practice, it might take a whole lot more than 3. Okay, that was just an example to get us used to being able to analyze the concept. All right? But in a real system, what if it took, instead of taking 3, what if it took like 10 or 12 or something like that? Man, can you imagine how much time you'd be spending just waiting? So the problem is the CPU would spend many cycles waiting for memory reads. So here's what we do. In the same way that using that 2-byte data bus, we pre-fetch and then use what was pre-fetched later on. That's the main idea behind a cache. What we do is, when we fetch something from memory, we don't just fetch the byte or the word. We fetch a whole big chunk. A whole big chunk. And we store it in a high-speed cache that's physically closer to the CPU so that it doesn't have to go over the system bus. And then the next time we need some, and so what we have is basically we have a copy of what's in memory. And then the next time we need something, we check to see if it's in the cache, and if it's in the cache, boom, we get it from the cache, and we've already prefetched it. We don't have to spend all that time waiting. That's the idea. But in order for this to work, we have to be able to predict the future. You see what I mean? Now here's the thing about predicting the future. Fortunately, in a typical program, it's you don't access stuff from main memory just randomly. In fact, why is it that, can you think of why it would be that if you fetch something, a byte from memory, that the probability is high that you're going to be fetching something that's either the same thing again or one that's close to it? Why would that be? Yeah, right next to, yeah, exactly. That's exactly right. So the programs typically have lines of programs that are all really close next to each other in address, because it's the next address, the next address, the next. Now, when does that? So whenever you're doing fetching, you normally fetch something that's really close to what you fetched before. When does that rule break down? When does that rule break?
If you're doing like a call, for example.
If you're doing a call. Right? So occasionally it will break, but in fact, here's the thing. If the memory references from the CPU were totally randomly distributed, then caching would not help. Caching only works because you have what is called locality of reference. Okay, and there's two kinds of locality of reference. There's spatial locality and there's temporal locality. And with spatial locality, the address close to the previously requested address is likely to be requested in the near future. And by the way, what about data? Suppose you're processing things in an array. Well, how is the data of an array stored? All contiguous. So as you're looping through and processing the values in an array, you know, they're all going to be close to each other. And why would you ever expect to get to need the same value that you fetched previously?
Well, maybe you're in a loop.
Ah, that's exactly right. Maybe you're in a loop. So and when you're in a loop, you're going to fetch boom, 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 and then you're going to go loop, fetch, boom, boom, boom. You're going to get boom, fetch. So if you can get all the statements that are in the loop in the cache, as you're going through, you're fetching. Yeah, that's exactly right. So that's the idea. That's why it works, and that's the idea. Now, in practice, it's not just the memory over here and the CPU over here, and there's just one cache in between. Because look, if it helps to have one cache in between that has, you know, not as much memory as the main memory, but is a lot faster, what about between the cache? What about between the memory and the cache? You could do another cache. So you could like cache the cache. Do you see what I'm saying? And so in practice, there are it's very common to have at least 3, sometimes 4 different levels of cache. And these are called L1, L2, and L3. And by the way, you guys, when you go to buy a computer, and if you look at the technical specs, are you familiar with this terminology? I bet you could look up the technical specs for an Apple computer right now, and it would give you information about how big the L1 cache is, and maybe even the L2, because they use this as a marketing feature. You can market your processors this way, or if you look up the Intel chip. So typically these caches are denoted L1, L2, and L3. And L1 is the one that's closest to the CPU and the smallest and the fastest. And then L2 is bigger than L1 but a little bit slower. And L3 is bigger than L2 but a little bit slower, but still faster than main memory. Did you find it?
Yeah, it's.
Yeah, what does it say?
So it's gone up to.
Okay, so here, let's quote that here. So look here at figure 12.27. First of all, what happens is in all modern processors now, they're all multi-core. So that means more than one CPU. And so here in figure 12.27 is a typical, you see the dashed line around the big, all that stuff? That's one chip. So like, in the lab when we have the chips and the Motorola chip that we saw the other day, well, 4 processors on one of those chips. All right, and furthermore, the L1 cache and the L2 unified cache and the L3 unified cache are all on that chip. And look at how they're designed. What happens is each CPU has its own L1 cache, but it has a separate cache for memory and for data. Do you see what I mean? So that's what's called a split cache. That's why it's called split L1 instruction and data, smallest, fastest, closest to the CPU. And then there is an L2 unified cache. Now unified means stores both what and what? Unified means stores both what and? Yeah, both data and instructions.
Yeah, because it's not.
It's not, yeah. Are you with me? And typically what happens is each core has its own L2 unified cache, and then typically the chip as itself has a big what? L3 unified cache that then interfaces with memory. Are you with me? So now, what were those figures that you had that they advertised? So they were telling you 256K for this L2 unified.
Yeah.
Did they give the other specs?
It was
3 megabytes for the L3, yeah. Did they say anything about the split cache or no? They didn't get that much detail?
It doesn't say.
Yeah, well. Oh, for the i7 chip, yeah. 64K for the what? For the L1? Yeah. So there's some specs. So see, they advertise, this is how they advertise it. And just to show you how tiny the PEP9 is, the entire memory of PEP9 is what? It's a 16-bit computer. The entire memory is what? 64K. The entire memory of PEP9 is 64K. That the whole thing fits in one little cache. So it's really tiny. It's not, the size is very not, realistic, but the concepts that it illustrates are all very realistic. The concepts are, yeah. Yes. Oh, yeah. Okay, so what happens is it's different memory technology. What happens is the way the engineers, the way the circuits work, the circuit designs work, is the faster you can make the memory, the more space it takes. Literally the numbers of transistors. And I will say that it's the memory model that we used in the previous chapter. Do you remember when we talked about SRAM, static RAM? Static RAM is the fastest, but it takes the most real estate on the chip. And that's where each one is like a D flip-flop. Each bit is like a D flip-flop. Okay, and then different memory technologies have different speeds and take up different amounts of real estate. And it's always the case that the smaller that you can make the real estate, the slower the memory is. And that's and so there's a spectrum. There's, between, it's one thing when you talk about the total capacity and the other thing talking about how much real estate it takes on the chip. So if you are willing to expend more real estate on the chip for a given memory capacity, you can make it fast. Again, it's the space-time trade-off. Yes, L1s are smaller but faster. L2s have more capacity but are slower than L1s. And L3 are slower than L2 but have bigger capacity. And main memory has all the capacity that you would ever want in your whole thing, but it's slow, really slow.
L2.
Well, okay, yeah, that's a good question. What determines the speed? The thing that determines the speed is what's called the hit ratio. So So it depends on all. It depends on all three of them. The total performance depends on all the levels of the cache.
Because they have to go through L3.
Because you literally have to go through. Yeah, it seems like it might slow things down, but the thing of it is that if you get here, let's take a look at what the cache operation is, and we'll see how this plays out. So here's what happens. When the CPU requests a load from memory, it first checks the cache. A cache hit occurs if the requested data is in the cache. Are you with me? And so it can fetch from the cache immediately and not have to do that memory thing. Right? A cache miss occurs if the requested data is not in the cache. Then you have to fetch it from main memory. Or the next slower cache. But the same thing happens with that cache. If it's there, it can give it to the next hierarchy, the lower level cache. Are you with me? But if not, it has to go to the next cache. And if it's not there, it has to go to memory. So when your computer first boots up, and have you noticed how it can be kind of slow to get, once it, when all of your applications are loading for the first time and you open that application for the first time, why is it so slow? It's going through all those levels of cache and getting the memory and getting it, but once those caches get filled up, then boom, it can, that's a noticeable effect, right, with your computers. So now there are two types of cache design. There's what's called direct mapped cache and set associative cache. And we're going to start with the direct mapped cache. Now, in the direct mapped cache, what happens is the physical address is divided into three fields. Okay, there is a high order tag field, a line field, and a low order byte field. You guys have all had data structures, right? And do you guys remember the hash table? What happened in a hash table? How does a hash table work? You remember we would store it
Based on a hash function.
based on a hash function. And why did we need a hash function? But why did we have to have those chains? Do you guys not remember this?
You're talking about like collisions?
Collisions. Yeah, remember it was collisions? Right. So what happened is you had this huge address space. Okay, but your hash table was only this big, and there'd be all these possibilities. But what might happen is one key might do what? Might be hashed to here. Another key might do what? Might hash to here. But then another key might do what? It might hash to the same thing as this. And why did that happen? Because all the possible values of keys, we couldn't afford the space to have the array have one index, each key have its own index in the array. But don't you see, that's exactly what we have here. What we have is, this is just a hardware version of a hash table. Because what we have here is, we have a small memory subsystem in the cache that's smaller than main memory, but if we're going to prefetch, we can't, it's not as big as main memory. So what does that mean can happen in a cache? That means that we're going to have several different memory locations are going to be mapped to the same memory location in the cache itself.
So there's collisions in the cache?
So there's collisions. Collisions can occur. It's the exact same phenomenon, but it's at the hardware level instead of being at the software level. So memory is divided into lines or blocks, and when one byte is requested on a cache miss, the entire line containing the byte is loaded into the cache. So here is the basic figure. It's figure 12.28 that shows how this works at the hardware level. So we can see in this particular example, the address is the block in the upper left-hand corner of the figure, and it's divided into tag, line, and byte. So the tag is 9 bits, the line is 3 bits, the byte is 4 bits. So 9 plus 3 is 10, 11, 12, and then 4 is 16. So this is a 16-bit computer. So this is like PEP9, right? Very small. Are you with me? So those fields are called tag, line, and byte. And on the right-hand side, you see what we have a picture of main memory. Are you with me on this? And those addresses are in decimal instead of in hex, but we'll just put them in decimal. And look, each one of those is a line. So how many bytes do we have in each line? How many bytes do we have in each line of memory? Well, look, what's the 16. 16. There's 16 bytes, right? Here it is on the bottom, 16 bytes. So the address of the first line is 0, and then 16, and then 32, and then 48, and then 64. Are you with me? Okay. Now, what does the CPU do? The CPU requests an address, requests a byte from an address in main memory. So as far as the CPU is concerned, the cache is invisible. The CPU is, all the CPU knows is that when it does load byte accumulator, it's going to get something from memory at that byte, and everything else is invisible at the CPU's, as far as the CPU is concerned. So what has to happen is the cache subsystem takes that request and fills it. And how does it do it? What it does is, in this particular cache, there are, how many entries are there in the cache? And they're in the middle. 8, addressed what to what? 0 to 7. And so, do you see then that how many bits does it take to have a range of 0 to 7? How many bits does it take to have a range from 0 to 7? To be able, 3 bits. 000, 001, 010, 010, 011, 100, 101, 110, 111. Right? It takes 3 bits to have a range from 0 to 7. So do you see then that what this cache subsystem does is it divides the memory request, the address of the memory request from the CPU, it divides it into 3 fields. And what it does is the first 9 bits are called the tag field, the 3 next bits are called the line field, and the last 4 bits are called the byte field. And because there are 7 possibilities for what's in the line field, those are the 7 entries in the cache. So each entry of the cache, so there are 8 entries in the cache addressed from 0 to 7. And whenever you access one, instead of just accessing 1 byte from memory, how many bytes does this access from memory at a single request? If the PEP9 wants 1 byte, instead of just getting 1 byte, how much does the cache? How much does it get according to this scheme?
16.
It gets 16, all 16. The one that it requests might be in the middle, it might be near the left, it might be the right, but it's going to get all 16, and what it requests is going to be in that 16. So it's going to take those 16 and it's going to pull them into the cache. Well, where in the cache is it going to put them? That depends on what the bits in the line field were. Yeah, question? Yeah, you're right. So what has to happen is the design has to be compatible. The width of the cache has to be compatible with the width of the data bus. So what happens is every memory access is going to take 16 bytes, and so it's prefetching. Do you see what I mean? Using locality of reference. Okay, and what it's going to do is, so do you see that the byte at address 0 is going to go into the cache entry at 0 cache entry, because the line will be 0. Now what about 16? Let's suppose that the memory wants from address 19. Let's suppose that the CPU wants the byte at address 19. What is 19 in binary? Oh, can we do 19 real quick in binary? 19 divided by 2 is what? 9 carry your what? 1. 9 is what? 4, carry your 1. 2, carry your 0. 1, carry your 0. 0, carry your 1. Is that right?
Yep.
So I think it's 1, 0, 0, 1, 1. Is that right? Is this 19? That's 19. Okay, so look. So this is 19, so here, let's do it over here. 1, 0, 0, 1, 1. So this is 19, but now how many bits do we have? 16 altogether. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so look. What is the tag part? 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. So does everybody see that this is the tag? And what is the line part? 0, 0, 1. And what is the byte part? 0, 0, 0, 1. So what it's going to do is, so what is this? It is going to take which? It's going to take that one at address 16. It's going to take a chunk from 16 to 31. And where is it going to put it? Where is it going to put it in the cache? At what location? At 001. So do you see then that it's going to go right here? That data, this is 16 bytes of data, is going to go right here. Are you with me? And then what's it going to store? So the data is going to go there, and then what's going to, and then what else? What's going to go here?
001.
No, actually, what's going to go there is 0, 0, 0, 0, 0, 0, 0, 0, 0. Are you with me? And then the tag field, and then there's an extra bit called the valid bit that is set to 1 because now we know that there's information in there from main memory. So that's what the valid tag field does. It tells the system that we have loaded, this contains the copy of something in memory. This is the address. The data is what goes, the data from memory is what goes into the data field. Now you have an assignment that's due Monday on this, but we're obviously going to have to postpone it for a day, and we'll finish this up on Monday. All right. See you next time.